Good evening, all. Sorry for yeah. Good evening, all. As the class is already started and you forgot to start the camera, so we can start the class again. Okay. So sorry for the technical error. So welcome back to the NPTEL online certification course Biophotonics program for 2024 January to April session. Um, your TA for the course. My name is Jijit. I am an interdisciplinary research scholar of IIT Madras for chemistry and biotechnology, and I am a graduate in physics. Okay, let us start the session by saying the some normal theories and techniques which is actually useful to learn about the courses. Okay, and this is actually my week 8 session, and I am thinking you people are already gone through the week 8 lectures, and this is actually we will discuss here the model questions which is provided by NPTEL only, and week 8 program. And as you may be already aware that yeah, this week 8 program is mainly telling about the photodynamic therapy, and we will discuss and this assignment questions as I go through, and we can see that these are like direct questions mainly. So instead of going through the questions of the assignments directly, I'm planning to go through the theory parts, some basic concepts of the light matter interaction which may be useful for you people to understand the main concept of this photodynamic therapy. And as we already told, this photodynamic therapy is a medical field. This is a method. The thing is that for solving these assignments, actually, you don't need to know the basics also. And this question, assignment questions are direct questions, but this may be useful to understand you people to know the concept for solving some more type questions, and so some practical oriented questions or application oriented questions, etc. So we will start with the saying about some light matter interactions, and we will discuss some basic concepts from that one, and this will be like very elementary concept, but that will be some useful for understanding the concept as well as so solving this assignment questions as well as the other things. Okay, just start. Just wait for a minute. I'll start my presentation. So let us start a presentation. So can start some basic elementary concept of light matter interactions. So here we will deal with some light matters and the basic light matter interactions and how they are working. Okay. So now first we will deal with the light matter interaction which we are seeing in the normal world. Like what happens when a light is actually interacted with some particles. So first we will go and check what happens when a light is interacting with the opaque particle. What is an opaque particle? An opaque particle is or opaque material is a material in which the it will not allow the light to travel through it. So what happens when light rays are coming? If this is an opaque material, there will not be any light ray after these particles. So you can see that here there will be light particle, light will be coming, not light particle. So light rays, and you can say yeah. For this light matter interaction, like basic light matter interaction, you need only particle nature of the light. So if you are saying that a beam of light is coming and if it's incident on an opaque particle and that you can see that there will not be any light which is after this material and this kind of particle is called opaque materials. And you can see that there are transparent materials. What is transparent materials? So there will be some light is coming here. You can see some light here also. They may not be exactly same as here because there will be some interaction happen from this light to this material and there will be some light is coming here that you can see that will deal with what will be happen if the light is incident on a transparent material. And now we will see that what are the things affected. So what happens to an object? So this is opaque, this is transparent. Just wait for some time. Hello. ഓട്ടോക്ലേവ് ആരെങ്കിലും വെച്ചിട്ടുണ്ടാ സാധനം വെച്ചിട്ടുണ്ടാ ആക്ച്വലി ഞാൻ ഇപ്പൊ NPTEL ഡ്യൂട്ടിക്ക് ഞാൻ എന്റെ ഹോസ്റ്റലിൽ വന്നിട്ടല്ലേ ഞാൻ പുഷ്പാന്തരായിട്ട് വിളിക്കാം ഞാൻ ജസ്റ്റ് ആ ആ ആ ആ ആ ആ Hey, where are you? Hey, somebody kept autoplay. Uh, I don't know. They somebody if they just inform him and they just go and check it because something is happening there. Either that pressure leaking or some pressure is going or something is going because this Akshay called me. Okay. Okay. Let's continue our session. So what happens? Light is incidenting on an opaque substance. So opaque substance anything like a leaf or a mm, stone or anything. So what we are actually seeing the opaque substance as some colored substance. So leaf is like green and stone is something red kind of thing. And how it is happening. So how we are seeing an opaque substance. So what happens? There will be a source of light. Let it be a white light source. So it is emitting all the wavelength. So light is incidenting on the opaque substance. What happens? Some light is getting reflected, and this reflected light is actually we are seeing through our eyes. So if it is an opaque substance, what happens? This containing all the wavelength. So it's like a white light containing all the wavelength. All all the wavelength in the sense that all wavelengths which we can pursue in the form of vision. So so it containing all the wavelengths starting from 400 nanometer to 700 nanometer, which is actually violet to red. Violet to red. This will be geo, and it will be like around 400 to 700 nanometer. The whole together, the spectrum of this whole together is actually detected by other cells in our eyes, and actually we are seeing it as a white light source. Okay. So what happens when it is incidenting here? There will be like different molecules and other things. When we are saying that this is like a red brick or something, what happens? This containing some substance such that it will absorb. So it will absorb some light from the incident light, and that emitted light will containing only the red components and some might nearby that one. So when the white light is actually passing here, this is getting absorbed by some light and it is reflecting, and the reflected light which is reaching our eye containing, it is actually exciting or that it is helping our eye corn cells or rod cells to distinguish the color. Rod cells are used for seeing the color of dim light, and for this black and red white color differentiation, the rod cells are useful, and cone cells are actually used for seeing in bright light and for the color perception. So a opaque object is visible in the form of a color when, except that color, all the lights are actually absorbed by that substance. Except the color means the color through which, and only the color in which that substance is visible is actually emitted. not sorry, it's not, it should not be used the term emission. Yeah, it's only reflect. So there is actually we are seeing here two kind of phenomenon, which is called one is absorption, another called reflection. And you people are already see that when we are dealing with the reflection, we say that okay, light is coming here, it's hitting and it's reflecting, and the reflection from a mirror, it's like we are seeing some object, even though it is coming here and it's exactly reflecting all the rays similar manner. So this kind of reflection in which all the rays are getting reflected in a proper manner and some image is actually visible, like we are seeing the our own face on a mirror. That kind of reflection is called specular reflection. And reflection from some irregular surface and other things, actually we are not seeing any proper image kind of thing, like yeah, reflection from a stone, we are not seeing any image of the source or something there. Or reflection from a leaf, we are only seeing the features on the leaf only, we are not seeing any features which is actually as a reflected image in the leaf. So this kind of reflection, the reflection from a regular surface, this is called a diffused reflection. And this diffused reflection cannot make a proper image. The specular reflection can make a proper image. So we understood the two phenomena, one is absorption and one is reflection. Similar way, we can see what happens when a light will hit on a transparent object. So if it's hit on a transparent object, what happens is some portion will reflect back, some portion will pass through this, and some of the light may get absorbed by this substance. So there's a reflection and there is an absorption, and this passing of the light from one medium to another medium, and it passes through that one is actually called the transmission. So there will be some incident light which is coming here. Some light is go back by reflection, and some light will come as a transmission, and some light is actually absorbed by that particular material or the thing. So you can see that the transmitted light will be a combination after removing this reflected component as well as this absorbed component. So that's why we are seeing that sometimes this transmitted light will be much diminished because the most the energy or the photons are actually absorbed by the material itself. Now we can see, so we see that there's a phenomenon called reflection that's mainly happening because of that interaction with the surface. And there's a phenomenon called transmission. And this transmission is happening because of it is interacting with the inner molecules, and the light which is unaffected, you can say unaffected, means that it is not interacting with the directly, or it is not getting absorbed. And that absorbed light is actually coming out. Okay, so this absorption actually makes a important role in our thing. So if we see the molecular level of absorption, what is actually happening in the absorption, you can see that if you see the molecular energy level, or the we call it as a Jablonski diagram. It is a energy distribution diagram showing different molecular energy levels of a material. So the lower energy state is called ground state, and these are like upper energy level states, and these are actually coming as a result of the quantum mechanical calculations. So You can see that these energy states are actually quantized, but they will be like very nearly overlapped kind of things, such that sometimes it may appear in the form of a continuous state also. But if we look in a careful manner, we can see that these all energy levels are actually quantized. So, what happens when a light is incident on a material? So, if the light containing a wavelength which is actually matching with the energy gap between two states, usually the ground state and the excited state, what happens? The material can actually absorb the light, and the electron will go from ground state to excited state, exciting excited by the light. So what is happening here? So here light is consumed by the material and the energy of the material is got increased. From here it can again go back to ground system by either in a non-radiative manner or by emitting a photon. And if it is going back by emitting a photon, that particular phenomenon is called the fluorescence. And if that is actually going in a non-radiative manner, we are actually the that energy of the electron, which is actually came from the energy of the photon, is actually, we can say that that is converted to some thermal energy kind of thing, and we will not see that any emission from that particular system. Okay, so this is the absorption. So, so then there are two phenomena like fluorescence. If the excited molecule is going back to its ground state by emitting a particular photon, that phenomenon is called fluorescence. Usually, what happens, there will be some excited state level, and this excited state level also have different energy levels. So, from ground state, it is actually excited to some excited state. From there, it is coming back to the lower energy level of the excited state, and from there, it is getting de-excited with the emission of the photon. Okay, 1 minute. Sorry for the technical issues. I will let's continue our thing. So yeah, so we can see that when a light is interacting with the a material, when it is getting absorbed, the ground state electron is actually getting excited to this higher excited state. From there will be some transition. This it's called non-radiative transition, in which it will come at the lower energy state of the excited energy level. From there, what happens? The electron is actually transferred to the ground state, and as a result, there is a emission of wavelength is happening, emission of photon is happening. And now see that this is the this much energy is used for excitation, and there will be some energy loss or loss in the form of the photon, which is happening because of the non-radiative transition. And as a result, what happens? The incident light will have a shorter wavelength, because this is the higher energy level. Higher energy level is proportional to E is equal to C by lambda, or E is proportional to 1 by lambda. So if energy is higher, lambda will be smaller. So the excited photon will have a shorter wavelength compared to that emitted light, and that phenomenon is called fluorescence. So this is happening in the case of a normal absorption in a material. Some There are other transitions also. So this is like a singlet transition, and there is a chance that and this non-radiative transition, in which the higher energy levels of the excited state is coming towards this lowest energy level of the excited state is called internal conversion. This is a non-radiative transition method conversion. So there are like this is a singlet state transition, which is actually quantum mechanically possible, and there can be some transition from the excited state. Electrons can go to triplet energy level, which is actually a triplet transition, which is actually quantum mechanically forbidden transition. So mm, the what do you call? So the possibility is also less, and the thing is that the chance of going triplet transition is much less compared to the single transition, but the possibilities are also less. But it has a more lifetime compared with the lowest energy state of the electron. So from the triplet transition, it can go to ground state with the emission of some photon, and this process it will take more time, because this triplet energy state is actually some more have the electrons in the triplet energy level will have a more lifetime compared to that singlet electrons at the lowest energy state of the excited state. So as a result, it will take some more time. And this kind of emission, the emission which is followed by the triplet state transition, is called phosphorescence, and the singlet state transition is called fluorescence. Okay, these are the interactions which is happening in the molecular level. Now we can see that what happens when a light is actually passing through some material. Let's see, this is somehow transparent, and the light is coming. Some light is actually getting transferred, and some of the light is actually absorbed by the system. If it is a emission and it can give some fluorescence material, fluorescence properties, you see there is no emission is happening. Some light is only, now we are only considering with the transmitted light. So the incident light and the transmitted light we are considering. So what happens here? So just consider this as a monochromatic light. Some interaction is happening, and as a result, some light is actually transferred. So this is called the absorption of the light by a system, and the energy or the light intensity. If you consider light intensity, I is equal to I naught e raised to minus epsilon c. This is the relation. So this law is called Beer-Lambert's law. What is saying? It is saying that intensity is actually when it is passing through. So just consider the same. This is incident light has an intensity of I naught. So what happens? This will exponentially decrease. And this epsilon is actually a constant which is actually depends on the material in which is actually the absorbing entity. Let's say particular constants called molar absorption coefficient, and C is actually called a concentration of this material. So if there's a liquid particle, so this will be a concentration of the material, and L is actually a length of the material. So this is called the Beer-Lambert's law, and the ratio of I naught by I ln is called the ln I naught by I will be epsilon CL. If you are taking say common logarithm like 2.303 log I naught by I, it will be epsilon CL, and this log I naught by I is equal to epsilon by 2.303 CL. This quantity, or we can say this log I naught by I is called the absorption of the optical density or absorbance. This log I naught by I is called the absorbance of the material. And it's a ratio, the log of a ratio. So it does not have any unit. And we can say that absorbance will be equal to some capital epsilon naught CL. Well, this epsilon will be epsilon by 2.303. This will be a constant. This is called molar absorption coefficient. C is the concentration of the particle, and length is the length of that entity. And this is actually called Beer-Lambert's law. And Beer-Lambert's law is actually coming from this equation. I is equal to I naught epsilon e raised to epsilon C. Okay. So these things are actually useful when we are dealing with the photodynamic therapy. So these are like some basic concepts which is actually useful when we are studying the photodynamic therapy, and we will see how we can use this method by seeing the assignment problems. Okay. So let us actually do the assignment questions. So the first question, this is a direct question which I've actually deal in the classroom. Basal cell carcinoma is a type of, the question is a breast cancer, blood cancer, bone cancer, or a skin cancer. And yeah, this is actually discussed in the class, in which we can see this is a cancer which can be dealt with the photodynamic therapy, and this is a type of skin cancer. Okay, so the option of this question is actually B, so skin cancer. Okay, this, yeah, you can see these assignment questions are almost like a direct questions if you have go through this lecture as well as some materials. So you can actually see all these questions are straightforward type. There is no much problem solving kind of questions, so there is actually, it will not take much time to complete your assignments also, and to understand this kind of questions. So this basic concept what I discussed today will be actually useful to understand the concept. But yeah, even though when you are not directly seeing this is happening here, but these are the things actually it is happening here. So in the case of a photodynamic therapy, we can see that what they are doing, there will be some chemicals. There will be, so just say that you have a body. So this body will have a some malignant growth or something. Sorry, look like a heart. Sorry. Okay. This is the malignant growth inside the body. So what we will do, so we are going, let it be this on a skin or it's something esophageal gut or something, this growth. So so we are going to apply this medicine either through infusion or as in the form of some medicine, or as externally or some method we are applying this medicine or applying the medicine inside the body. So let it say it is infused. So this is medicine. So what happens? It will go through your body and it will actually got uniformly throughout your body because of normal blood circulation. But this body or this medicine has a capacity to specifically bind to the cells which is actually malignant in nature. So what happens during the incubation time or the waiting time? What will happen? These things will go, This thing will go here and accumulate around the malignant tissue. Now this medicine is also somewhat non-harmful, so there is not a much problem for this one. So what happens? This is now the medicine is in the form of an inactive form. What happens? Then we will start our photodynamic therapy. So using some fiber optics or something, we will some optical fiber or something. What we are doing, we will pass some laser light so that exposure depends on that how much time it will take to get activated and how much energy it should be required for making this medicine to be active and how much damage it will make the cells. These kind of things we have to take consideration when you are doing this one. So what happens when this light is getting thing and there is a strong interaction between this light and these molecules start in the active form and it may produce some free radicals and other things. So as a result, what happens? It will actually destroy the cells in this portion and the cells are actually malignant in nature is actually bind with this kind of medicine which is inactive in the normal form but it is become active and free radical giving kind of things when it is in the active form when it's exposed with the light with a particular frequency and power. So what happens as a result, the cells are destroyed and your that particular tumor is got destroyed and the cure will happen. There will be some side effect also there. So there will be some minimal damage to the cells towards that region, and that will be cured during the time course. So this is the way it is happening. So these are actually effective for different types of skin cancers, different cancers in mouth, esophagus, and other things. So and even that will be useful for doing treatment to the more inner part also. Why? Because we can actually give the medicine will go and accumulate there, and with the minimum openings, actually we can pass an optical fiber which will carry the light which is used to activate your medicine. So this is like it will make a minimal damage to your body. Okay, let's move to the second question. Photodynamic therapy of leukemia is known as so it's also a direct question. The answer is extracorporeal photopheresis. So the answer is A. So photodynamic therapy of leukemia is known as extracorporeal photopheresis. Photopheresis. Okay. The light source for photodynamic therapy should be selected on the basis of photosensitizer absorption. Now we see whether that can be true or not. So there will be a photosensitizer, which is actually which we are using one of the main content of our medicine, what are you calling it as a medicine that will be containing a proper photosensitizer. So why we want a photosensitizer? When a light is irradiated, the photosensitizer should interact with the light and it should absorb the light, and it will become some active molecule which will actually create a lot of free radicals, either in the form of oxygen free radical or in the form of a OH free radical. So which will be useful for destroying the cells in which attached with the sensitivities method. So the the light source wavelength as well as the absorption wavelength of our photosensitizer should be matched, and only the proper absorption will happen. So photosensitizer absorption is a possible answer. Now, size of the tumor, the light source, and the size of the tumor. So the thing is that the source should be capable of give the proper wavelength light to the proper areas of the tumor. So if the tumor size is small, actually you can give a small sized source such that it will not affect the other part of the body. Even though we are saying that this light is non-harmful, there can be some side effect can be caused by these laser sources, because these are some high powered laser sources. So in order to make the exposure minimal to that tumor area only, the source area should be selected. So the size of the tumor actually can be one of the possible answer. But yeah, while you seeing this, the two answer is correct, we can directly see that. So now the third question is the location of the tumor. So yeah, we have to direct the light source to the tumor location such that, and there's one more thing is also, because this photodynamic therapy, the light is actually penetrates around like 2 to 3 mm depth if we are using in the normal mode. So the light source should be reached within the vicinity of the 2 to 3 mm of the tumor. So the location of the tumor also matters. So you can see the A, B, C are matters, then the correct answer will be the D, which is showing all of them. Okay. So the answer for the question is option D, which is all of them. So the next question: an ideal photosensitizing agent should be a single pure compound, good stability in storage, both A and P, D, none of this. So it's also seems like that way. It should be a pure compound also, and it should have a strong stability in storage also. So so that answer for this question is actually C, saying both A and B. Okay. A radiation-less process in which the singlet excited electronic state makes a transition to a triplet excited state is known as. That actually we discussed sometimes earlier. So you can see that. So from the ground state to the singlet excited state. That's during this absorption, electrons are exciting, and from here it is coming to the lowest energy state of the singlet excited state. And this phenomenon is called the internal conversion. That is a singlet to singlet transition only. Now there can be a transition in which from this singlet excited state electron can transfer to the triplet excited state, and this phenomenon is called intersystem process. Okay, so the answer is B, which is making the answer correct, and the answer is intersystem process. Okay. So the next question is: A ALA can be used to treat. So it's also direct question from the classes. So this is a answer is nothing but a basal cell carcinoma. So these are like direct questions, so there is no need of explanation. Okay, the answer is A, which is called basal cell carcinoma. A program in which a cell death process where except a plasma membrane, every cell organelles breakdown is known as. So this is one method in which the cell organelles are getting breakdown, and there will be some another method. These are like a different methods to destroy a cell, so that cell organelles can be breakdown, or the cell even the plasma membrane can break down. If the plasma membrane is breaking down, you can call that as a necrosis. But in the case of a cell organelle is getting breakdown, that is called a apoptosis. Okay, so the answer is the question is the advantage of using laser as a light source for photodynamic therapy. Now, in the olden days, what actually usually in the photodynamic therapy, what is actually needed, we say that photodynamic therapy is in that method. There's a photosensitizer. Photosensitizer is getting attached to a cell, some particular cell, and when it's actually radiated with the light, the sensitizer is getting activated, and this will destroy the cell. This is actually the photodynamic therapies method. So in olden days, what they used is like a normal incandescent lamp is actually enough to give the photodynamic therapy, because the coherence of that wave is not that much matter, because this is actually like a normal absorption. The photosensitizer attached with the cell will absorb the molecule and get it activated. So normal light is actually enough for this photodynamic therapy. But the advantage of using a light as a photodynamic therapy is because actually you can, in the case of incandescent lamp, what happens in a normal incandescent lamp, we cannot actually give the particular spectrum. We say that this photosensitizer will have a spectral band at which it will actually absorb the light maximum and get activated. So, for example, if that absorption range is something like a 1024, we don't have to excite the molecule with like a broad range of wavelength, because that other wavelength actually does not have any effect on that particular molecule, and it will only loss of power, as well as it may create some extra damage or some burn to the area where we are actually exposed. So actually, if that particular have a particular wavelength range, so it's like a laser with a proper wavelength can be used. So the monochromaticity of the laser is actually good for doing that one. The second one, broad field irradiation. So that's actually, if you are using an incandescent lamp, actually you cannot control the, if there's an up some aperture is there, you can control the irradiation using that aperture. Otherwise, the light from a normal lamp will actually go in all the possible directions. So the broad field of irradiation is not at all a matter of a laser light, but it is actually a property of the incandescent lamp. Okay, so broad spectral width. So that also similar thing. So usually the normal incandescent lamp have a broad spectral width, but in the case of a laser, usually laser will have a very sharp spectral line. So spectral width will be in the frequency domain. So in the case of a in the case of an incandescent lamp, it will have a broad spectral width. But in the case of a laser, you will have, so this will be around like 400 to 700 nanometer wavelength will be there for some laser. What will have, it will have a narrow spectral width, just make it a more monochromatic. More monochromatic makes a narrow spectral width. So this is also not the property of a laser, but the property of incandescent. Large beam divergence. One of the property of the laser beam is that when the laser is actually emitting from the source, it can go over a long distance in the parallel manner. So the divergence of the beam is less. In the other case of an incandescent lamp, what happens? The light will go diverge in a very fast. So the largest beam divergence is also a property of a incandescent lamp, not the laser. So the proper answer is here. Is only one answer. That is the advantage of using laser as a light source in the photodynamic thermal. It's a highly monochromatic. And the other method also, this a less field of irradiation. So we can use actually very small area we can choose, and we can specifically destroy the cells in that area. So that's actually one of the good thing about the laser. Whatever we are seeing, it's not a broad field irradiation, it's a narrow field irradiation. In the case of spectral width is also for the laser, the spectral width is small. That's actually give the purity of the, or the monochromaticity of the wavelength. So it will be specific to that particular photosensitizer, and it will not create any unnecessary radiation of the other wavelength to the cells. So this also property. And large beam divergence. So what happens in the case of the beam is getting divergent faster, the penetration capacity of the beam will be go less. But when the beam is actually going in a parallel manner, it can properly irradiate and can transfer properly to the area where the photosensitizer is attached with the cells, which should be destroyed. So that also the lasers have the property that it has a narrow beam divergence, and that also will increase the effectiveness of the photodynamic therapy. The typical output power is essential for efficient photodynamic therapy. This is a direct question which can be answered if you see the lectures. For the photodynamic therapy using porphyrin is actually comes like a 1 to 2 watt. Nanoscale materials is typically used in photothermal therapy. So yeah, these are like photothermal therapy is something like in which that the interacted light with the material will create a thermal effect at the surface. So you can see what are the things which can be used for this thermal effect. So this gold nanoparticle is a very good thing for this doing this. Since it has a plasmonic effect, it can be used as a good nanoscale gold nanoparticles are actually good for this photothermal therapy. So gold nanoparticle is actually good. And the graphene is also, it has a strong confined electronic system. Actually, graphene also can be used as an agent of a photothermal thermal. So the answer comes as both A and B. So this is the answer. So in this today's class, actually, what we dealt with, we actually go through the different aspects of light matter interaction, and we see how the common materials are. We saw the different aspects of light matter interactions, and we saw how the common materials are transparent or opaque, and how we are seeing the transparent material, how we see the opaque material, and what makes a transparent materials as well as this opaque materials colored, and the phenomenon of absorption, reflection, and what happens when a transparent material is transmits some color through that material, and some absorption is causing, and the intensity of the incident light and intensity of transparent light is actually depends on the material property and the thickness of the material, and that is actually given by the relation of Lambert's law, and the molecular level idea of this absorption, emission, internal conversion, intersystem crossing, fluorescence and phosphorescence kind of things, and in a global sense, how Lambert's law can be expressed, and the concept of absorbance. And then actually we go through the different aspects of the assignments, which is actually dealt with the photodynamic therapy. So hope these things are actually useful for you people. And if you have any doubt and any further clarification required, actually you can do posting in our Google groups. Our TA will go through that way and try to give proper solution for that one. And if you have people have any other doubts or some more clarification required this one, you please try to contact us. So consider it as a enjoyment journey to understand how photonics and biology is go in hand. So hopefully this session is actually useful for you people, and thank you for watching, and let us meet next week. Thank you. So I am going to close the session. So if you have any doubt, you please mail us such that it might be your doubts. Thank you.